In calculus, integration by substitution, also known as u-substitution, is a method for finding integrals. Using the fundamental theorem of calculus often requires finding an antiderivative. For this and other reasons, integration by substitution is an important tool in mathematics. It is the counterpart to the chain rule of differentiation. Substitution for single variable. Definition: let I be an interval and phi a, b, I be a continuously differentiable function. Suppose that f I is a continuous function. Then in other notation, the substitution x equals phi yields dx dt equals phi, and thus, formally, dx equals phi dt, which is the required substitution for dx. The formula is used to transform one integral into another integral that is easier to compute. Thus, the formula can be used from left to right or from right to left in order to simplify a given integral. When used in the latter manner, it is sometimes known as u-substitution or w-substitution. Proof: integration by substitution can be derived from the fundamental theorem of calculus as follows. Let f and phi be two functions satisfying the above hypothesis that f is continuous on I and phi is continuous on the closed interval a, b. Then the function f phi is also continuous on a, b. Hence the integrals and in fact exist, and it remains to show that they are equal. Since f is continuous, it has an antiderivative f. The composite function f phi is then defined. Since f and phi are differentiable, the chain rule gives applying the fundamental theorem of calculus twice gives, which is the substitution rule. Examples: Example 1. From right to left, consider the integral. If we apply the formula from right to left and make the substitution u equals x2 plus 1, we obtain u equals 2x dx, and hence x dx equals 1/2 du. It is important to note that since the lower limit x equals 0 was replaced with u equals 2 plus 1 equals 1, and the upper limit x equals 2 replaced with u equals 22 plus 1 equals 5, a transformation back into terms of x was unnecessary. Example 2. From left to right. For the integral, the formula needs to be used from left to right. The substitution x equals sin dx equals cos du is useful, because the resulting integral can be computed using integration by parts or a double-angle formula followed by one more substitution. One can also note that the function being integrated is the upper right quarter of a circle with a radius of 1, and hence integrating the upper right quarter from 0 to 1 is the geometric equivalent to the area of 1/4 of the unit circle, or pi. 4. Example 3. Antiderivatives. Substitution can be used to determine antiderivatives. One chooses a relation between x and u, determines the corresponding relation between dx and du by differentiating, and performs the substitutions. An antiderivative for the substituted function can hopefully be determined. The original substitution between u and x is then undone. Similar to our first example above, we can determine the following antiderivative with this method, where c is an arbitrary constant of integration. Note that there were no integral boundaries to transform, but in the last step we had to revert the original substitution u equals x2 plus 1. Substitution for multiple variables. One may also use substitution when integrating functions of several variables. Here the substitution function equals phi needs to be injective and continuously differentiable, and the differentials transform as where det denotes the determinant of the Jacobian matrix containing the partial derivatives of phi. This formula expresses the fact that the absolute value of the determinant of a matrix equals the volume of the parallelotope spanned by its columns, or rows. More precisely, the change of variables formula is stated in the next theorem. Theorem: let U be an open set in Rn and phi. Urn an injective differentiable function with continuous partial derivatives, the Jacobian of which is non-zero for every x in U. Then for any real-valued, compactly supported, continuous function f, with support contained in phi. The conditions on the theorem can be weakened in various ways. First, The requirement that phi be continuously differentiable can be replaced by the weaker assumption that phi be merely differentiable and have a continuous inverse. This is guaranteed to hold if phi is continuously differentiable by the inverse function theorem. Alternatively, the requirement that det 0 can be eliminated by applying Sard's theorem. For Lebesgue measurable functions, the theorem can be stated in the following form. Theorem. Let U be a measurable subset of Rn and phi. Urn an injective function, and suppose for every x in U there exists phi in Rn, n such that phi equals phi plus O as yx. Then phi is measurable, and for any real-valued function f defined on phi, in the sense that if either integral exists, then so does the other one, and they have the same value. Another very general version in measure theory is the following. Theorem. Let X be a locally compact Hausdorff space equipped with a finite radon measure μ, and let Y be a sigma compact Hausdorff space with a sigma finite radon measure ρ. Let phi xy be a continuous and absolutely continuous function, equals 0 whenever μ equals 0. Then there exists a real-valued Borel measurable function W on X such that for every Lebesgue integrable function f, the function W is Lebesgue integrable on X, and furthermore, it is possible to write for some Borel measurable function G on Y. In geometric measure theory, integration by substitution is used with Lipschitz functions. A bi-Lipschitz function is a Lipschitz function phi Urn which is 1-to-1, and such that its inverse function phi minus 1, phi u is also Lipschitz. By Rademacher's theorem, a bi-Lipschitz mapping is differentiable almost everywhere. In particular, the Jacobian determinant of a bi-Lipschitz mapping det d phi is well defined almost everywhere. The following result then holds. Theorem. Let U be an open subset of Rn and phi. Urn be a bi-Lipschitz mapping. Let f, phi r be measurable. Then in the sense that if either integral exists, then so does the other one, and they have the same value. The above theorem was first proposed by Euler when he developed the notion of double integrals in 1769, although generalized to triple integrals by Lagrange in 1773, and used by Legendre, Laplace, Gauss, and first generalized to n variables by Mikhail Ostrogradsky in 1836, it resisted a fully rigorous formal proof for a surprisingly long time, and was first satisfactorily resolved 125 years later, by Elik-Artin in a series of papers beginning in the mid-1890s. Application in probability. Substitution can be used to answer the following important question in probability. Given a random variable with probability density and another random variable related to by the equation, what is the probability density for? It is easiest to answer this question by first answering a slightly different question. What is the probability that takes a value in some particular subset? Denote this probability. Of course, if it has probability density, then the answer is, but this isn't really useful because we don't know py, it's what we're trying to find in the first place. We can make progress by considering the problem in the variable takes a value in S whenever x takes a value in. So changing from variable x to y gives combining this with our first equation gives so in the case where and depend on several uncorrelated variables, i.e., and can be found by substitution in several variables discussed above.